Greetings friends. The previous video I cut into two parts because it had too much information which could land me in trouble. So I'm redoing the second part with less pertinent information. Okay, the discussion was on IDDQ. In the previous video, I explained what IDDQ is and how it is tested. I now want to move deeper into parametric testing of IDDQ. IDDQ, IPD, all the parametric tests are roughly the same. The same applies to everything. Okay, behind me over there, you will see a silicon wafer. Okay, on the silicon wafer, you'll start probing, shall we say, you'll start probing and you'll go in a row. And you'll go all the way along and you'll snake all the way up. Snake all the way up. Okay. Okay. Now, what you'll find is that the XY location of the die has a lot to do with the amount of current and its analog leakage currents that you'll find. Here you'll find low leakage, and as you get closer to the center of the wafer, you will get higher leakage. Okay. In my experience, this area here, which I'm talking about, will have the highest level of leakage, at least on the wafers that I tested. Okay, so what is the problem? The problem is that if you want to use a limit which will be acceptable for the center of the wafer, you may send bad dyes at the edge of the wafer. You might not catch the error. Okay, so what was done? Okay, I've got two documents here which speak about this XY relationship with parametric tests. Okay, and as far as parametric tests are reliability, I think I discussed how a device can be functional and still be bad. Okay. Okay, so what was done? What was done at Fab 8 where I worked was they took a moving average of the first few dyes on the wafer and created an average. The average was weighted so that the previous dye had more weight than the dyes before that. The reason being is you want a relatively quick response. Okay. Okay. So the result of this was on the first die on the third wafer, on the third row, would almost always fail. The first die on the row would, and afterwards the eyes would pass. Let's call it the sacrificial lamb, Sir Lazazel. Okay, your first die on the row would fail, and after that you would have next dies would pass. Okay. So what would happen is this way, this row would pass, this row would pass, this row, the third row, this is a half a die, the first row here, the first die would automatically fail, and what would happen is this would push the limit up. As it pushed the limit up, the next dies down the road would all pass. So you'd have almost a 100% failure of this XY location. Okay, one die which was sacrificed for the yield of the wafer. Okay, this is the way it was done. You don't have to like it. I didn't like the solution. I couldn't believe the differences in values between the bottom dies and the center of the wafer as far as leakage current was concerned. I'm not a physicist, and I don't exactly know why. I just took it from the test results, and I couldn't understand how we were sending these dies out as automotive, but that's a side issue. Okay. How did I want to fix this issue? I wanted to fix this issue in a different way. I wanted to take the statistical values, the average values of dies that had passed over 2,500 wafers, which is 100 lots. If I take the statistical value of 2,500 wafers, I would be able to create a limit, an XY limit for each parameter. Okay, so if I know that I'm expecting this XY location to be higher than the beginning, I can put in a factor. This was something I worked on at the end of, I was working on it roughly 2003, 2004. After I got lynched in a review, I destroyed everything I'd worked on. This was something I was doing around 2003, 2004. Okay. I even told my then group leader Avi Levy, I'm destroying everything I'm working on, because this was not done under the auspices of Intel. This was my own private thing I was working on, as well as I was working at the same time on calibration, but I stopped. There's a price to pay when you lynch a person in a review. Okay. I stopped doing this. Okay. So what I was doing, I went back 2,500 wafers, production wafers, and tried to work out a scaling value for parametric values on the wafer. This was not the way it was done. It was done in the way of a moving average. It was not done in the way I wanted to do it. It was done in the other way. Okay. When you do it, when you do it in the way of a moving average, okay, one of the shortfalls is that your first dies on the wafer. Your first dies on the wafer, you've got no average to check them against. The way it worked was the average was reset every single wafer. You didn't pass across the limits from the previous wafer. It was done from the start at the beginning of every wafer. So that means the first values, the first dies on the wafer were done at a limit which was not representative. Okay, the limit was, if I remember correctly, was very high. So it was almost impossible to fail IDDQ at the beginning of the wafer. Okay. It was later on that hole was blocked. How was it blocked? The end of the wafer, they would do, it was called offline testing, where the values were, the whole wafer was evaluated off the off the tester, not at the test limit. Okay. Next issue is that if you're going to create your limits via a moving average, it's almost impossible to detect a shift in the process. If your values are going up and down, your values are going to go up and down. And if you're not that on the ball, you'll slip up and you will miss a change in the process, which could be catastrophic. Okay. So my solution was somewhat different because I wanted to implement it on all the parametric tests, not only on IDDQ. I wanted to do it on all parametric tests because I felt that this type of mechanism, I think I even saw it on some of the other tests, like IPD. This is IDDQ. The same mechanism would be in play. Okay. If I'd have a matrix of an XY matrix with correction factors for the limit, it would have added a different level of safety. One, when you had the process shift, you would have detected the process shifted. You wouldn't have landed up in the facepalm moments when devices returned from the customer, and you ask yourself, how on earth did we send this out? Okay. I don't want to go into more detail because that was the reason why I edited that out of the last video. Okay, so if I'm looking at it here, the risks are that you don't, because your values are always shifting and not fixed, you don't detect the shift. Okay. Second thing is that in order to that if I see a device which failed in the field and I remeasure it, okay, it doesn't really apply to this particular product. This particular product was a flash product where you could actually, where the XY location was burnt into the flash at some secret place, so one could actually detect where it was on the XY, but there was no way of knowing what the test limit was on this particular die without going back and digging into the whole wafer and trying to see the previous dies, what were their values. Therefore, I know what this value is, the test limit here. I couldn't see a die and say, this is the test limit. Even with my method, you can't do that. But you can, you can't pick out a die and say, this die was tested and passed IDDQ with this limit. Okay. I personally think my solution was a lot better. It was not implemented. I was never asked for my idea on this testing. Besides the fact I didn't like the way the test was implemented. Okay. This is the censored version. Thank you for your time.